So good afternoon. Thanks a lot. So I'm very happy to introduce some key results about this Nanofactory project. So more or less the key aspects of this project is to integrate robotics inside of the room of a scanning electron microscope, to play with that and to manipulate, to bring some manipulation, characterization on assembly techniques inside of this scanning electron microscope. So while we are doing that, we can see that there are, there are many applications where many people in many fields need to build some complex architecture, complex devices, especially in 3D. So this is true in the field of optics with this kind of devices that results in the piling up of slice for the controlling the propagation of light, or people that wants to who want to structure, functionalize the tip of an optical fiber, or the people also in the mechanical field who like to develop or study small wires or stuff like this, especially here, for example, scientists like to functionalize the tip of an atomic force microscope. So in all cases, many questions happen, so we would like always to build more complex devices, but also to know to control the manipulation, assembly, characterizing, being able to characterize that. So here, there are many ways to do that. We want to do that by the ways of using robotics. Nanorobotics does not mean nanoscale robotics, but it means robotics that can act at the nanoscale. So all the stuff we are working on are around the micrometer in size, in terms of object to be manipulated. And we are bringing the robots to bring a contact between the robot and the object, and to collect some information, to bring the sensor the closest of the area of interest, to be able to bring a deformation, for example, and also to understand the behavior of the system through physical modeling, for instance. So how to do that? So the key point is using of a scanning electron microscope, the specific part is here. This is the room of the chamber of the scanning electron microscope, which is very big because we want to introduce some equipment inside, robotics, sensors, and so on. The second key aspect is the control shelf that you can see here, because most of the things we have are commercially available on the shelf, but not the control system. The control system that is behind here clearly intends to be able to synchronize all the stuff inside of the scanning electron microscope. And we could see here some views of the human-machine interface that has been also homemade. The interest is that people who are not pure roboticists can achieve very complex tasks based on robotics with high accuracy without being specialist of robotics. So I'm sorry, I don't know why it's switched like this. I try not to press the button. So here we can see all the equipment that are inside of this microrobotics platform. Among them, we can see there are 4 kinds of robots. Everything except this one is on the shelf and commercially available. This last one has been designed for the basic specification we gave in order to reach large motion in a very confined space, because inside of this scanning electron microscope, we don't have lots of space. So everything, if we summarize the things, so we can achieve many tasks, such as cutting the material, making some assemblies, piling some structures, bringing some measurements, and doing very complex assemblies or tasks with very different materials in 3D. So the 2 key points are we want to bring control for that, to control the robots in an accurate way and in a dynamic way. So we have 2 technologies that pays attention to for us. We have the robots that are usually commercially available. We strongly believe that there are very strong limitations, notably in terms of the way they achieve the motion. So we also studied new ways of generating motion with robots. So first point, so we developed this own-made control system. Here on the right, we have the controller on the computer, the worker program the machine with that. We have all the systems that are working on the machine, and we have all this homemade interface on this complex architecture enables to synchronize everything and to work in real time. So this is why we can work with dual hands, and we can achieve many complex tasks with that. So now we want to study the ways to achieve complex motion, large motion with high accuracy using this commercially available system. So the robots at the micro and nano scale, we can see they have very large imperfections, even if they are sold to have nanometer resolution. The accuracy, their capability to reach the good position we want is very limited. So we developed a principle based on using the image from the scanning electron microscope, which is planar image, and we move using the robot in a reference way. This a sphere that is used in the middle as an object to be tracked. And building many images, we can identify many imperfections of the robot. Then, because they are repeatable, we can compensate their effects. At the end, we demonstrated that doing strong efforts, meaning 1 on half year of postdoc, we can get in 6 degrees of freedom a typical positioning accuracy of around 10 to 15 micrometers for most of the tasks, but doing large motion. So for us, this is the typical limitation. To break this barrier and to go beyond this 10 to 15 micrometers, we worked on a new way to provide to generate the motion. So commercially available systems, it's very simple. So either they have very large workspace, meaning they can achieve a very large motion, or they can be very accurate, but in this case, they have very small workspace. So among all the technologies that are used, that are available, so we could notice one that pay a lot of attention for us. This is the Continuum Robots. Continuum Robots, they recently paid a lot of attention, especially for the medical field, where we want to go inside, for example, of the body with very small aperture, but we want to do very large motion. Okay, so here this platform is the thing that is moved. It's suspended by some wires, and the unbending of the wires is moved by an actuator. And by moving this unbending of the wires, then we can move this platform in the space. And all there are not so many studies about that, but all the studies already demonstrate a very large interest for the medical field, because this robot can bring large workspace. For us, because this is the physical principle is based on the continuum deformation of these beams, then we were strongly thinking that it could also be a very good candidate for high accuracy. So we studied that through a PhD study. So we notably developed a demonstrator where we have this mobile platform that is suspended by these continuum legs. And here we have the actuators at the end. The key question about that is we want to control the motion, so it relies on the the mechanical model of the robot. And for that, we always need to make a trade-off between the complexity of the model and the positioning accuracy we will reach. So in most cases, in state-of-the-art, people always try to use a simple model so that they can identify in reality, experimentally, the parameters of this model, and then the problem, they do not demonstrate the accuracy, and they cannot reach that. So we wanted to push by far the limits of this robot in terms of positioning accuracy. So we choose complex modeling, very rich modeling, but the question happened about how to identify the parameters. So to solve that issue, we place some patterns on some specific location of the robot, and the pattern could bring an intermediate measurement with very high position to resolution ratio. So this is a technology that we master very well in our lab. And it could enable to combine some parameters that were directly measured and optimization algorithms that could conduct to identify the remaining parameters. Based on that, we could demonstrate for the first time in the state of the art 2 key points. Continuum robots, they are a very suitable solution for achieving positioning accuracy with the micrometer level. And we can also, we also demonstrated the achievement of complex mobilities, complex tasks at the microscale. So we use that. During the project and also now beyond the Nanofactory project with several partnerships. For example, here we worked with the Thales group. Here they have many systems that are based on the growing of carbon nanotube perpendicular to the substrate. And they paid a lot of attention to our robotic stuff, and we could bring them some electrical measurements of the resistivity of this carbon nanotube on site, and we can discriminate the resistivity of the electrical connection, but also make measurements all along the tube, which helped them a lot to improve their fabrication process. So we also are working on the characterization of fibers, either plant fibers or synthetic fibers, through the ways of these robotic aspects. And we are also working on the optical and nanophotonics proof of concept with interesting architecture together with the optics lab in FEMTEST. So to summarize, we worked in this project mainly about control, how to bring the dynamic control and robot control, how to synchronize many tasks together, so that we can really bring many functionalities together in the same volume in this room of the scanning electron microscope. Reason why we say this is really a nanofactory. And for the future, we are working on many kinds of ideas, but among the ones that are very interesting is we want to build some complex structure like this, but that are not passive, that becomes active. So that can, for example, complex structure like this house that could be moving, transforming the shape. And for example, also other structures like this that are based on optics, for example, that could be used for robotics purpose like this kind of gripper, or for application point of view like this nanophotonic system. So I want to thank you, and if you have questions, I would be happy for that.
Thank you. So is there any question? So it's not easy for me to ask a question because I work in the same team. So I have almost the response of the question I may ask. So I can ask a question, but you may also ask your own question. You may just say some word on so in fact it's a bit between, you are a part of a scientific project, but also a platform beyond. You may say some word maybe on the how to access to the platform. It could be interesting from some of the people in the room.
Yeah. So So for this platform, so it's let's say an open platform. So if someone is interested to make an experiment or to bring his devices so that we could see and to do some manipulation, characterization, then it's no problem. It's one of the objectives of this platform. To give the access to external people, but also to bring to the help and the expertise so that the things can be done, let's say, during the afternoon, during the coming days, very rapidly and with good quality. And we are building the Micro Nanorobotics Center, which this platform will be part of that. And more generally, we will bring robotic solutions that are not commercially available. So it means that we don't want to develop things alone. We need to develop things for specific needs, together with people from the chemistry field, biology field, and so on, to bring tools, robot tools, that could help to do interesting studies or the production for industrial needs, for example.